about solar charging stations. Just like this one, this is just a representational image of a solar charging station where anyone can plug in their electric vehicles or any other devices like mobile phones or any other devices they want to charge. And these charging stations have each charging station has its own account on a blockchain network, and the network of these charging stations is fully decentralized, which means that there is no centralized authority maintaining these charging stations, and all the payment processing happens directly between the user and the charging station itself. So each user transacts with the charging station through a mobile application and sends a payment from his or her own wallet to the charging station's blockchain account, and then the charging station gets activated for the duration according to how much amount has been paid to the charging station. So for this case study, we will create our own virtual currency called solar coins. So solar coins is just a virtual currency which we'll create, and any user can purchase solar coins by paying in the ether cryptocurrency, which is native cryptocurrency specific to the ethereum network. And then users can send transactions to the charging stations from a mobile application and also through a decentralized application, web-based decentralized application. So I'll be showing two interfaces, one using a mobile application and other using a web-based decentralized application. And next, once a user sends a transaction to the charging station, it gets validated and processed on the Ethereum blockchain, and then the charging station gets activated. So there is an IoT device which is connected to the charging station, which continuously checks for the status of any payments which are made to the charging station. And whenever a payment is made, the charging station gets activated for a particular duration, and then automatically gets deactivated. So this is the architecture of the solar charging station. So what we have here is we have a blockchain network on which the smart contract for solar charging stations is deployed. So we have one smart contract through which we can manage multiple charging stations and users. So users have to register with the smart contract and make payment in the form of ethers to get their own solar coins, and then they can use the solar coins to make payments to the charging stations to activate the charging stations. And each charging station has its own account which is managed through this smart contract, and we define a particular rate for each charging station. So how much solar coins have to be paid to activate each charging station for let's say 1 minute. So per minute rate for every charging station can be different based on at which location the charging station is deployed. So we can set different rates, and then user scans the QR code of the charging station from his mobile application and makes a payment. So we have a blockchain network, and I will demonstrate two types of networks. I will demonstrate a public Ethereum network and also a private network. So let's say we don't want to use a public Ethereum network, and we just want to create our own private network only for the purpose of this case study, or only for the purpose of these charging stations. Then we can set up our own private network as well. So the process, the steps here is firstly a user, who is also the owner of the contract, he deploys a smart contract on the blockchain, and this smart contract, the solar charging stations smart contract, it manages all the user registrations and setting up all the accounts for the charging stations and defining the rate of each charging station. And then the contract owner adds stations to the contracts. So we send transactions to the contract by providing details of each charging station, where the charging station is deployed, the location of the charging station, a unique ID specific to the charging station, how much rate per minute the charging station has, and other details are provided. And then user adds each charging station to the contract. And then other users can register with the smart contract associated with the charging stations. So anyone who wants to activate a charging station, they can register with the smart contract, or they can directly use a mobile application, which is much more user friendly. And then users purchase solar coins by paying in ether to the smart contract through a mobile application, and then send transactions to charging stations by paying in solar coins. So each user approaches a charging station, scans the QR code from mobile application, makes a payment in solar coins, and when the charging station gets activated, the user can connect the electric vehicle or any other device they want to charge. And then we have an IoT device which is continuously monitoring the status of the smart contract associated with the charging station. And once there is a payment, new payment, which is processed specific to the charging station, the IoT device activates the charging station. So this is a representation of the smart contract. So what we have here is we have a user who is the owner of the smart contract, and user sends a contract creation transaction from the user's externally owned account. So to deploy the contract, user uses his externally owned account, deploys the contract on the blockchain network, and then once the contract is deployed, all the other users also send transactions to the contract, register themselves with the contract, and then pay to the contract by sending certain value. And then we have the IoT device which checks for the balance associated with the device, and if there is any payment, new payment being made, the device gets activated. So these are the various entities involved in the representation of the smart contract. We have state variables, functions, modifiers, events within the smart contract. So I'll be going through the implementation details of the smart contract. And this is just a representation of this charging station, all the components involved. So I've implemented this charging station using a solar panel, a relay which is connected to the solar panel, and then we have a BeagleBone Black, or we can use Raspberry Pi. Any single board computer device can be used. And this single board computer, it is monitoring the status of transactions on blockchain network. And whenever new payment is done to the contract, the BeagleBone Black activates the relay, which activates the charging station. So this is the actual prototype with the BeagleBone Black, a relay module, universal plug where you can plug in your devices, and a QR code attached to the charging station. And let's look at the demo of the mobile application. Then first I'll show you the demo, and then I will go through all the implementation details. So what we have here is a SolarCharge mobile application, which I've developed along with my colleagues at Georgia Tech. So user logs into the application. And each user has a wallet account in the application, which shows the user's solar coin balance. So now, as you can see, this is showing the user's solar coin balance. So user's name, email, blockchain address, the amount the user has paid, and the solar coin balance is shown. Next, if a user wants to charge any device, user scans a QR code, or either scans a QR code or enters the address of the charging station manually. So each charging station has a unique ID, which can be entered manually, or you can scan a QR code. So let's say a user scans the QR code. So here we scan the QR code. And once the QR code is scanned, the application will retrieve the details of the charging station from the smart contract. Since each charging station is registered with the smart contract, we have the station ID, location, and the rate per minute in solar coins. It is displayed to the user. So for charging any device, we have to pay 10 solar coins per minute. And then the user specifies the number of minutes to charge. So let's say user wants to charge the device for 1 minute, and then user pays the charging station. So it shows it will charge user 10 solar coins and then confirms the transaction. So after the user confirms the transaction, it is sent to the blockchain network. It is processed and mined on the network. So this part of the demo, it shows the mobile application. Now let's look at the demo of the actual device. So this is the demo of the actual device. So what we have here is we have a BeagleBone Black device, a relay module, universal plug. It is monitoring the status of contract. Now, once a user makes a payment, see that this got activated. The relay module got activated, and the connected plug got activated. Now, user can plug in the device and charge it. So it will remain active for a certain duration, and now it got deactivated. So, what is the benefit of setting up such a system using blockchain, and how does it differ from a centralized system? So, this system differs from any centralized system because we have these charging stations are deployed in a fully decentralized manner. Each charging station has its own account. Users are paying directly to the charging station's account, unless unlike a centralized system where a user has to make payment to through a payment gateway to a company's bank account or a company's wallet account. Here, there is no centralized authority involved. The charging stations are fully autonomous in nature. So we'll look at some implementation details. So before that, I would like to discuss one more important aspect of blockchain network types. So as we see here, there are two dimensions. The blockchain networks either they can be permissioned or permissionless, or they can on the other dimension we have public and private. So we can have various possibilities of blockchain networks. We can have private permission networks, private permissionless networks, public permission, and public permissionless networks. So what does that mean? A private permission network is the network in which only the members of a particular group or a consortium they can join and validate the transaction. So it is private to a closed group. So let's say your organization or college or university sets up a private permission network, and only the faculty and students are allowed to join. So that is a private permission network. Then we can have a public permissionless network, which is the complete opposite of that. That means networks like Bitcoin and Ethereum, they are public and permissionless, which by which we mean that anyone can join the network and anyone can validate and process transactions on the network. So these networks are uh, the users are kept anonymous, and they are fully decentralized in nature. So public permissionless. Similarly, we have public permissioned. So the network is public, but who is allowed to join is determined by certain criteria. So anyone who meets a predefined criteria can join the network and validate the transactions in a public permission. Similarly, in private permissionless, we have the network is private, and there is no permission required as such. So for this case study, what I'm going to show today is I'm going to deploy this same smart contract firstly on a private blockchain network, which I will set up using the Parity Ethereum client. So we will demonstrate a private permission type of setting. And also I will deploy the same contract on a public permissionless network, which is the Ethereum network. So we look at both types of deployments of the same contract. So let's get started with the looking at the implementation details. So firstly, we look at the contract, smart contract. So this smart contract, it's implemented using the Solidity programming language, which is very similar to JavaScript language, and it's not it's quite easy to understand. So how we implement a smart contract? So as we see here, we have a contract. We provide a name to the contract. So we call this solar charger contract, and we have two structures. So one struct is maintaining records of users. So we maintain record of user name, the address of the user, the amount paid by the user, and the balance of user in terms of solar coins. So all these items are maintained within one user structure. And then we maintain a mapping from the user's email address to the user structure. So if we provide the email address of the user as the input, which is a byte 32 field, then we can retrieve the user's structure. Similarly, we have a struct for station, the charging station, where we define the rate, which is an integer, location, the balance of the charging station, when it was last activated, and the last activation duration. So how much duration the station remained active. And then again, we have a mapping from the station ID to the structure of stations. So by providing a station ID, you can retrieve the struct specific to a particular station. Then we have some other public variables within the contract. For example, the owner of the contract. Who is the owner? We record the address. Number of users who have registered with the contract. Number of stations which are registered with the contract, and the coin rate. So coin rate is the solar coin rate. So how many ether you have to pay to get one solar coin. So this is configurable. So now when the smart contract is deployed, we have a constructor for the smart contract, which is this, it has the same name as the smart contract. So we have the solar charger contract, and then we have a function by the same name, solar charger. And in this constructor, we provide, so when a user is deploying this smart contract, this function will be executed. So what a user has to provide certain input variables which are required by the constructor. So in this case, the constructor is not using any input variables. So all the uh, initialization variables, they are hard coded in the contract itself. But you can actually make it more configurable. You can ask the coin rate to be provided at the time of deploying the contract. So the user who sends the transaction to deploy the contract becomes the owner of the contract, and there is a special variable within Solidity called the message. MSG is a special variable which has records of, for example, who is sending the contract. So message.sender returns the address of the person who sent the transaction. So when a user is deploying the transaction, message.sender will return the address of the person who is sending the transaction, and he becomes the owner of the contract. So we record the address of the owner as the person who is sending the transaction, and then owner has certain privileges. Only certain actions or certain transactions can be done only by the user. So we restrict access to certain functions to only the user of the contract, or the only the owner of the contract. Now we have number of functions. Let's say we have a function to register a new user. So how a user can register with the contract? They can provide their email address as input and their name, and then we create a new structure, user type user, and record the address of the user, which is the message.sender. So any user who is sending a transaction to register user function of the smart contract, their address will be can be retrieved from this message.sender variable, and then we record the address within the user structure. Similarly, we record the name, amount paid by the user, their solar coin balance, which is initially 0. So we set these values to be 0, and then we increment the total number of users within the smart contract by 1, because one more user has registered. Next, a user buys a solar coin by sending a transaction to this buy coins function. So in this function, we have defined this function as public and payable. So by defining this function as payable, anyone can send a payment to this function. So when you send a transaction to any smart contract or any specific function of a smart contract, you have to provide certain input variables, and additionally you can also send a value with the transaction in terms of the native cryptocurrency like ether. So by making this function payable, I can actually send ether to this particular function buy coins. So what happens if the user, so in this function I check whether the user account exists, and if there is no user account for this existing for this sender of this transaction, then I revert this transaction. So then this transaction gets nullified and the amount is refunded. Whereas if the user account exists, then I update the value of the total amount paid by the user in the user's structure, and also update the solar coin balance. So how many solar coin a user gets? The solar coin is the message dot value. So message, as I said, it's a special variable. Using message dot sender, you can get the address of the person sending the transaction. Message dot value returns the value which is sent along with the transaction, which is in terms of ether. So message dot value into my multiplied by my coin rate. So coin rate I defined initially, which is this rate. So that many solar coins are added to the user's balance. Similarly, we have other functions. We have function for adding a station. The owner of the contract can register new stations with the contract by providing the unique ID specific to the station, the rate, and the location. So again, we record those fields within the station's structure. And in this function, we see we are initially checking whether the message dot sender is not equal to owner. So if any other person is sending this transaction, then we revert it, because we want only the owner of the contract to add new stations. So like this, we can establish role-based access control by checking who is sending the transaction. So either only the owner is allowed to send this transaction, or only a close group of users may be allowed. Then we have a function to activate the station. How do we activate a station? A user sends a transaction to the activate station function by providing the email address, the ID of the user, the ID of the station, which has to be activated, and the duration. So these input variables are provided by a user by sending a transaction. And then in this function, we deduct that many amount of solar coins based on how much duration the uh, station has to be activated. We subtract the coins required, which is the rate of the station into the duration. So these are the coins required. And then we subtract the coins required from the user's balance and change the status of the station to activated. So when it was last activated is updated. So now is again a special variable. So if you specify now, it will return you this timestamp, current Unix timestamp. So like that, we make a payment to the station and activate the station. Then we have function for retrieving state of the station. It just you provide an ID, station ID. It will return you whether the station is active or not. Then we have function for retrieving the details of user. You provide an email address. It will return you all the details of the users: the username, account address, the amount paid, the solar coin balance. And finally, we have one function to retrieve the details of the station. So you provide the ID of station, it will return you the details of the station. So these are all the important functions in this smart contract. It's not very complex. It's like only a few lines of code. So let's get started with now deploying this smart contract. So how do we compile this smart contract? It is implemented in Solidity programming language. How do we compile this smart contract? And where do we deploy it? So let's say we want to deploy it to a local, a private permission blockchain network. So how do we set up our own private permission blockchain network? So we have a private Ethereum. We have an Ethereum client called Parity. So the Parity Ethereum client is there, and you can install Parity on your local machine, local laptop or desktop. And so these are in the instructions available. It's like you can set it up on your local machine, and then so how do we run our own private blockchain network for development purpose? So since I've already installed Parity, I can run my this Parity client, and we specify the chain. So Parity and hyphen hyphen dev will launch a development chain on my Parity hyphen hyphen chain, and then name of the chain, which is the development chain. So this runs a private development chain in which only my local machine is the participant. So this is a one node private development chain which I have created. And now I can deploy contracts to this chain and test my smart contract. So along with the name of the chain, there are some other parameters you have to provide because we want to enable access to the external applications. So, for example, some JSON, the RPC, and the process origin resource sharing settings have to be provided. So, why? Because I will be compiling the smart contract using a third-party tool. So now I've deployed this. I've started this private blockchain network on my local machine. And then if you go to remix.ethereum.org, it's a web-based tool which allows you to compile smart contracts and deploy smart contracts. So remix.ethereum.org, it's a web-based tool. And if you go to this tool, then you can create a new file and paste your smart contract here. So I've already pasted this smart contract into this tool. So this is my SolarCharger smart contract. And within this tool, you get the option of, firstly, we'll have to compile the smart contract. So on the first line of the smart contract, I have defined a pragma and I've provided a version of Solidity which is being used in this contract, because Solidity now has multiple versions. The language is evolving rapidly. So I'm using version 0.4.18. So I select that specific version from the compiler version list of versions here, and then I compile the contract. So now I'm compiling the contract. Okay, so this contract is now compiled. It gave me some warnings which are okay. Like these are like some security vulnerabilities it may have detected. So those can be fixed because I have made most of the functions as public. So by making a function as public, anyone can send a transaction. So it's giving me some warnings, but there are no errors. So it's fine. So now the compilation part is done. So what does compilation part gives me? It when you compile a Solidity contract, it will return you the it will return you two things. It will return you the abstract binary interface, which is the ABI. So I can copy the ABI here, and if I paste it, you will see this. This is the binary interface, the abstract binary interface. which is just the list of state variables and functions and their interface. For example, this get station is one function which outputs these types of variables. So it's just a like interface definition of that function, and it also returns me a bytecode. Bytecode is the compiled function, compiled contract. So this is the binary bytecode. So using the bytecode and the API, I can instantiate the function. So and then deploy this function. So how do I deploy the function and where do I deploy it? So if you go to this deploy and run transactions tab, you can select an environment. So it gives you various options to select the environment. You can either deploy it within this JavaScript virtual machine itself. It'll create its own sandbox environment, or you can deploy it on a particular blockchain. So now I want to deploy it on my private chain, which I just started on my laptop. So how do I connect Remix to my private blockchain network? For that, we need a special, we need a Chrome extension called MetaMask. So if you browse to the Chrome extensions page, or if you go to MetaMask, MetaMask is a Chrome extension by which you can connect your. So if you download this, it will install the Chrome extension, and I've already installed the Chrome extension. And in this Chrome extension, you can create multiple accounts like this. You can create an account. You will get an account address, and then you can connect the MetaMask to different blockchain networks. So from a list of networks, you can connect it to the main Ethereum network. You can connect to Ropsten test network, which is these are all the Ethereum test nets. Ropsten, Cohen, Rigby, and all the other. These are test nets. Or you can provide the address of the network which you want to connect to. For example, here I've already specified that I want to connect to my local machine. So if you go to settings in networks, you can add a new network type. So I've already added localhost port 8545. So that is my parity client is actually exposing an RPC over this port 8545. So localhost 8545 is my address of the RPC address of the blockchain network where I can connect. So if you browse to this Remix tool, then launch MetaMask. Firstly, it will ask you to log in. So you will have to log in. Once you set up MetaMask, it will ask you to sign up and log in, and then it will return you a number of accounts which are there on the blockchain network. So by default, there is one development account in this parity development chain, and this development account has a huge balance. This balance doesn't mean anything. It's just a virtual ether. They don't have any real value because you are running it on your own laptop. So this virtual currency doesn't have any real value. It's only for development purpose. So now let's say I want to deploy the contract from this development account. How do I deploy this? If you go to the deploy and run transactions tab and select the option as injected Web3. So this MetaMask will inject its own Web3 specific to the local network. So it's basically connecting your Remix tool to the local blockchain network, and then you select click on the deploy button, and then confirm the transaction. So now it says transaction is confirmed, and at the bottom you can see it shows me some details. It shows me the transaction hash, from which account the transaction was sent, and the other details. And then in the list of deployed contracts, you get this solar charger contract. You can see this contract has now been deployed. So this is the address of my contract. It has been deployed. And then I get a list of functions which I can send transactions to. So every smart contract will have a different functions, and this returns me a list of functions. So firstly, let's say I want to register an. Firstly, I will have to register a station. So how do I add a station to my contract? I provide a station ID. I specify a certain rate per minute and any location, and then send a transaction. So this transaction has to be sent from the same account who has deployed the contract. The owner can deploy this. So I confirm this, and then it says transaction is confirmed. So if I browse to my console, I can see you can see the transaction mined. So I sent two transactions. Firstly, to deploy the contract, so transaction has been mined, and secondly, to add a new station. So again, this transaction has been mined. So both these transactions have been mined. So what I have done till now, I have added a new station. So I can check whether my station has been added using the get station function. So you provide the station ID, and you press the call button. It will return you the details. So it returns me the rate, location, and the coin balance when it was last activated and last duration. So my station has now been registered. So next step is any user who wants to interact with the station, they can first register with the contract. So let's say I have a user. User provides an email address and a name, and the user can then transact. So I will select a different account here in MetaMask because I want to add a new user, and I will select a different account. So now I will send a transaction from another account, and I will confirm this. So this transaction got mined. It says transaction is mined. So that means my user has been added. So I can check by entering the email address of the user. So I can see the name of the user, the user's address, amount the user has paid, and the solar coin balance. So like this, you can interact with any smart contract using this interface. Now, let's say I want to pay to this smart contract and purchase solar coins. So how do I pay to this contract? So you specify the value here. So let's say I want to pay 0 0.1 ether, or I will pay. Okay, I will pay 1 ether, and I want to purchase solar coins. So I send a transaction to buy coins function. I provide my email address, and then send a transaction. So it says you are sending 1 ether to this address, and you confirm the transaction. So transaction got confirmed. You can see in the status it shows transaction mined. So now you can check your balance. If you go to the get user, if you go to this users function, you can provide the email address. It will return you your details. There's one more function, get user. So like this, you can interact and transact with the contract. You can, yeah. So this function get user, it returns you the amount paid. So I've paid 1 ether. So this is showing me 10 to power 18. So this unit is in V. V is a small unit of ether. So 1 ethereum is equal to 10 to power 18 V. WEI V. And I got these many number of solar coins. So finally, I can activate the station. So if you go to activate station, you provide the station ID 1234. Provide your email address, the station ID, and the duration. I want to activate it for 10 minutes. Then you send a transaction, and this transaction is sent and mined, and then you can check the status of the station. So get station state, it returns me true, which means now the station is active, and it will remain true or remain active for 10 minutes. So that was about the smart contract. So currently, what I demonstrated, I showed how to set up your own private development chain on your local machine using this Parity Ethereum client. I showed how to compile a Solidity smart contract using the Remix Ethereum tool. Then I showed how to deploy the contract by connecting this Remix tool to your Parity blockchain network through this MetaMask Chrome extension. And then we sent number of transactions to the smart contract. We send transactions to register a new station, register a new user, purchase solar coins, and activate a station. So now same thing can be done on any public network. So how do I transact and how do I deploy this contract on a public blockchain network? So I will stop this blockchain parity client. Now I will deploy this same thing on a public blockchain network. So in MetaMask, you can select which network you want to connect to. So Ethereum main network is the main chain, and here for sending any transaction, you will need real ether, and real ether actually costs real money. So 1 ether is almost equivalent to $200. So I will not use the main Ethereum network. Instead, I will use a test net. So we have two test nets, the Ropsten and Coven testnet. So any testnet you can use, and for testnet, you can get the testnet specific coins or testnet ether. These are again virtual ethers because this is only a testnet and it doesn't have any real value. And these testnet ethers can be acquired from any faucet. So if you go to, let's say, faucet.metamask.io, you can request 1 ether from faucet. So I just requested 1 ether from my faucet and it has sent 1 ether to my address, current address. So this is my current address and it has sent one testnet ether, which is specific only to this Ropsten testnet. So you can find many other faucets are available. So faucet is just a DApp which allow you to get virtual ethers specific to the testnets. And these testnets are public in nature. So just like the Ethereum main chain, these are also like public blockchain networks. The only difference is the value, the cryptocurrency associated with these networks doesn't have any real value. These are only for development purposes, but these are public, permissionless and public blockchain networks. So in the same way, you can select injected Web3, select the network as Ropsten or Coven, and then deploy the contract. So the same process we did for our private blockchain network can be done. And in the same way, you can deploy the contract. And in the same way, you can interact with the smart contract. So now moving on to the next part of our discussion, which is on uh, providing a user-friendly interface. So this interface is not very user-friendly because if you want users to interact with the smart contract and transact with the smart contract, they are not going to access remix and send transactions to the contract. It's not very user-friendly. It's only for the owners of the contract who can send the transactions. So what the end user wants, they want a very user-friendly way. So for that purpose, we have this. So I've developed this decentralized application or DApp. So what a DApp means? DApp or a decentralized application provides a user-friendly interface to the smart contract. So the same functions which we executed from this Remix client, Remix interface, same functions you can execute using this web application. So for example, you want to retrieve the details of a station. I just provide the station ID. I get the details of the station. Similarly, if you want to retrieve details of a user, so all these interactions with the smart contract can be done through the web interface. So what is a DApp and how it is developed? So DApp is basically just a web interface to the contract, and it's developed using HTML and JavaScript. So this is the HTML source code of the DApp, and this source code is actually available on my GitHub repository. So I will share you the link of my GitHub repository. So entire source code is available there. You can explore this later on. So we have an HTML page in which we have defined the various functions and input boxes, and all the functions are there and how what inputs have to be provided to each function. And then we have an associated JavaScript file. Within the JavaScript file, we provide the address of the contract where it is deployed. So this my smart contract is deployed on this address, and I provide the interface definition, that which is my ABI, the abstract binary interface, which I got when I deployed the when I compiled the contract. I got this ABI interface, and then I have functions for interacting with the contract. So these are JavaScript functions which will send transaction from your web interface to the blockchain network. So how does this web application connects to the blockchain network? That's through the Web3 JavaScript API, and this MetaMask extension acts as a bridge between your web interface, which is deployed on any web server, and your blockchain network. So that blockchain network can either be your private network or any other public permissionless network. So let's interact with this DApp from this browser. Let's say I want to firstly I will register a new user. So if so it asks me the account, and I confirm the transaction. And after a while, you can see this. This would be this transaction would be confirmed. So you can see the status of the transaction on EtherScan. So EtherScan is a tool where you can see all the transactions on any public Ethereum networks. So so we have an EtherScan specific to the Ropsten testnet, ropsten.etherscan.io, and you can see the status of the transaction. So we have this from address to address, value sent with the transaction, the gas limit, gas price, and the function which was executed. So I executed the register user function and the input values which were provided. So once this transaction is processed, since I'm sending this to a public network, it will take some time to get processed, and then you can repeat the same process. You can interact with the contract in the same way. You can register a user, buy coins. So now it is confirmed. So now I've registered this user. I will check, retrieve the details of the user. So get user, it shows me the details: user name, address, amount paid, and balance. Same way, you can send transactions, you can purchase coins. So let's say I want to pay. So I specified this value in V unit, which is 1 ether is equal to 10 to the power 18 V. So I provided a value 10 to the power 17, and which is zero point 0.1 ether. So I sent zero point 0.1 ether to the contract, and that will give me certain solar coin balance. So MetaMask also has a mobile application. So let me show you the mobile interface as well. So this is my mobile screen, and let me. If you go to the MetaMask Android application, MetaMask has a wallet and a browser. So wallet manages your balance and accounts. If you go to wallet, it shows my balance in Ether on the Ropsten testnet. So this value doesn't have any real. It doesn't have any real value. This Ether is just a virtual Ether. You can select which network you want to connect to. I will select Ropsten since my contract is deployed on Ropsten, and I have 4.87 Ether, which is equivalent to 963 US dollars. Just a virtual currency. It's not having real value as such. Then I go to browser, and you provide enter the address of your DApp. So where your DApp is deployed. So I've deployed it on one web server, and you will see the same interface which you saw from the browser. You can interact with this. Let's say I want to activate this station. I will provide a station ID, email address, and duration. So it asks me to confirm the transaction. I will confirm the transaction. Now the transaction has been submitted and it's waiting for confirmation. So you can actually browse to Ropsten, the Etherscan. You can see the status of the transactions. So this is my contract on Ropsten, and I can see all the transactions which are being sent to this contract. So you can see there is one pending transaction. This is the same transaction which I've sent from my mobile device. So it is still waiting for confirmation. Since it's a public chain, it will take few seconds to be processed. So like this, I showed you multiple ways of interacting with this smart contract. We deployed smart contract on a private blockchain network, which we set up using the Parity Ethereum client. Next, we deployed it on the public Ropsten test network, and we interacted with the smart contract uh, using the Remix interface, and we interacted with smart contract using the decentralized application DApp through a web browser and using the MetaMask. And finally, we interacted with the same contract using the MetaMask Android application. So there are multiple ways to interact. So now this transaction has been processed. The transaction is complete, and then I can retrieve the status, and you can see This station is now active. The last active duration is 1 minute, and this is the Unix timestamp when it was last activated. And station has its own balance, and this is the rate per minute. So this station has 22,000 solar coins, which have been paid to this station till now. So I think that's pretty much what I wanted to cover for this lecture. I wanted to demonstrate how we develop smart contracts, how we deploy decentralized applications, and how we interact with these smart contracts. What is public network? What is private network? What is permissionless network? How do we use MetaMask? Uh, how do we set up blockchain networks using parity? What is Ropsten and Cohen testnets? All those concepts I covered. So now I can take up your questions. And this source code for this case study is actually it's available on my GitHub repository. So if you go to github.com/arshdeep and then so I've actually made available the entire source code of all the examples in my blockchain applications book. So there are like this solar charging station was just one case study. So my book has like lot many other case studies are covered, and all the source code of all the examples are available freely. So this case study is covered in chapter 6. So if you go to chapter 6, and in this you will get the source code for this solar charger smart contract. And this case study is described in detail in this book. So you can refer to the GitHub repository. And also the instructor material is available on the book website. So on my book series website, like I've made available all the instructor material. So if you want lecture slides, source code of all my books, they are available from here. You can download lecture slides, source code, and request evaluation copies. Okay, so now I can take up your questions. There is a question: can a smart contract be used with IoT communication protocols? Yeah, so we use in this case study. I demonstrated how this IoT device accesses the status of the contract. So we deployed the contract on a blockchain network, and then we have an IoT device which is connecting to a server, and so we have a REST API between the server and the IoT device. So IoT device is sending a REST request to the server, which is also running an Ethereum node. So that server fetches the status of contract and sends a reply back to the IoT device. So source code of my examples of blockchain applications book is available on GitHub, but soft copy as such is not available. The You can purchase the paperback copy from Amazon, but soft copy is not released as such. So there is a question of how is the value of ether decided. So that's a good question. How do we decide value of ether? So we have various cryptocurrencies like Bitcoin, Ether, and which are traded in the market. And if you go to this coin market cap, you can see what is the current value of Bitcoin and Ether. So current value of Ether is now $197. It's currently being traded. So just like you trade stock, so we have trading exchanges for these cryptocurrencies, and their value keeps on changing every second based on their demand and supply. So if more number of users are deploying their contracts on Ethereum, and Ethereum network is being used by many decentralized applications. The demand for Ether will go up, and accordingly, the price for Ethereum, the Ether currency, will go up. So that's how the price is decided. And we have like thousands of other cryptocurrencies and blockchain networks. And Bitcoin, Ethereum are one of the most popular two networks. So there is a question on how to create, compile, and run file. So that's how I demonstrated. Using this remix tool, I created my smart contract, compiled it, and deployed it. And there is a question regarding this simulator. So I'm not aware of this simulator. Like I haven't used it. So example of IoT and blockchain in healthcare applications. Yeah, so there are multiple examples like maintaining patient records, a master patient index. Then for insurance applications are there. Uh, so one of the examples can be, let's say, monitoring the patient's health using a smart wearable device and sending the status to a blockchain. And then insurance companies can adjust the premium for the health insurance based on the monitoring of the user's health. Can blockchain Ethereum connect with any IoT related simulator? So it doesn't connect as such, like you will have to build your own connector or bridges. So you will have to implement your own REST APIs or create your own bridge. So for this case study, I created my own connector. I wrote my own REST APIs. Can transcript management of universities be implemented on private permission blockchain network? Exactly, yeah, you can do that. We can use private permission blockchain networks for managing certificates, transcripts, and these records can be maintained on blockchain networks. So, and there are many open projects. One specific project is from MIT, which is the BlockCerts project for issuing transcripts over the blockchain. So you can look up the BlockCerts project from MIT. So there is a